So now that we've discussed some basic reaction types, we can go into a little more detail on a specific kind of reaction that we'll be able to identify when we encounter it. All right, so as you see here, we have oxidation reduction reactions are the topic for this third part of Chapter 6 lectures. So unfortunately, these do tend to give beginning students some trouble, so make sure that you give them the attention they deserve. Try some practice problems. We'll do obviously some lecture checks here, learning checks throughout the lecture, but make sure to go and check the homework set questions, check some end of chapter questions. Make sure you're really comfortable with this topic because it does tend to cause some difficulties for students just starting out with the concept of oxidation reduction reactions. One of the reasons we talk about oxidation reduction reactions here in the course is because they are very common in life. Most of you I know are interested in the health sciences, and living systems do make heavy use of oxidation reduction reactions, but also we encounter them in everyday life as well. So we see here our iron-based tools, these steel tools rusting, and that's an oxidation reduction reaction. So how are we going to be able to identify these when we do encounter them? Well, in an oxidation reduction reaction, of course, electrons are transferred from one substance to another. So if one substance loses electrons, then another substance must gain electrons. We can't just have this buildup of electrons in nature. Nature prefers neutrality, and so if somebody's going to lose electrons, someone else is going to have to gain them. Energy is provided to us from food through our oxidation of that food, and therefore the accompanying reduction reactions. Electrical energy in batteries is a form of chemical potential that relies on oxidation reduction. If we're talking about primary batteries, then as they discharge, one portion, the anode, undergoes oxidation, and another portion, the cathode, undergoes reduction. And if you've ever inserted batteries into a device, you know the plus and minus ends. Well, those speak to those different processes. And then finally, as I already mentioned, iron rust. This is something that we know. Unfortunately, we probably know it from our own cars and other things that we wish wouldn't rust, but they do. The reaction we see at the bottom of the screen there, 4 iron atoms, or 4 moles of iron, plus 3 moles or 3 oxygen molecules react to form 2 moles or 2 formula units of iron 3 oxide, the typical red rusty solid that flakes off of those iron or steel instruments. Now, I've already warned you that this can be tricky, so we've got some things to help you out, some tricks to avoid the tricky oxidation reduction reactions. So first and foremost, we have the process of losing electrons is called oxidation. So oxidation is a loss of electrons, gives us the oil prefix, or if you prefer the zodiac, we have Leo says Gur, so loss of electrons is oxidation for the Leo part. And we see here zinc metal reacting to form zinc ion and produce 2 electrons. We also have the reduction process. That's the process of gaining electrons. So if we want to go with the oil rig mnemonic device, we can have reduction is a gain of electrons. So oil, oxidation is loss. Rig, reduction is gain. If you want to go back to that Leo says Gur, loss of electrons is oxidation for Leo, and Gur, gain of electrons, is reduction. So however you can keep it straight, whether oil rig works, whether Leo says Gur works, whether you come up with your own ridiculous sounding mnemonic, as long as it's meaningful to you and it gets you where you need to be, then so be it. No judgment here. And we see the reduction in this example is copper ion gaining 2 moles of electrons to form copper metal. And if you want to sort of have a picture in your mind of that whole process, we have here A plus B yielding A and B again, although of course they're a little different. A starts out with that electron visible that it transfers to B, so that on the product side we have A without that extra electron, and now B has that electron. So since A starts with the electron and then ends up on the side without it, that's oxidation. It lost an electron here. B starts out without the electron and gains it as we go to the product side, and therefore B is undergoing reduction, the gain of an electron in this case. So in that previous slide, we actually saw a visual representation of the electron being transferred. Another way to identify if something is a species that's either oxidized or reduced is to look at what we call oxidation numbers. So if we start at a less positive or a more negative number and we end at a more positive or less negative number, then that's an indication that we're undergoing oxidation if we have that move to the right on the number line here. If we go the other direction, we start at a more positive or less negative number and we end up more negative or less positive, that's indicative of a species undergoing reduction. So following those oxidation numbers from reactant side to product side is another way to identify the species that is oxidized or reduced in a redox reaction. So let's focus on this formation of calcium sulfide from the elements. So if we consider the reaction calcium metal plus sulfur is usually some sort of powder as a solid, goes to yield calcium sulfide, also a solid in the product phase, as we had solids on the left-hand side as well. So in this case, any element starting off as an element in a chemical reaction has a charge, an oxidation state actually of 0. In the product, we now have calcium with a 2+ and sulfur with a 2-, and we could predict that based on position in the table. We talked a few lectures ago, actually a few chapters ago, about metals tending to lose electrons to gain the noble gas configuration that precedes them. So calcium would lose those s orbital electrons in its valence, and therefore could develop a charge of +2. And that's indicative of oxidation, right? The calcium starts as calcium metal with a 0 oxidation number, and it reacts to form calcium ion with a 2+ charge, and then those 2 electrons. So as we go from 0 to +2 on the number line, we move to the right. That's an oxidation process. If instead we consider the sulfur, sulfur starts as well, just like calcium, as an element with an oxidation state of 0. And then if we look at the product, we have the sulfide ion, which now we have nonmetals tending to gain enough electrons to move to the noble gas that follows them. So sulfur's in group 16 or group 6A. It tends to gain 2 electrons to end up with a group 18 or group 8A noble gas configuration, and therefore develop a 2- charge. So if we go from 0 to -2 on the number line, that's moving to the left. That's indicative of reduction. So here we see that sulfur solid plus 2 electrons yields sulfide ion. So in that reaction, which we call an oxidation reduction, or redox for short, for reduction oxidation, we notice that the calcium is undergoing the oxidation process and the sulfur is undergoing the reduction process to make our product of calcium sulfide. Whenever we have an oxidation reduction reaction going on, we should have a net neutral charge to the whole reaction, because the species that's gaining the electrons and undergoing reduction should be exactly balanced by the species that's losing electrons and undergoing the oxidation process. So in this example, everything works very nicely because the calcium, elemental calcium that we start with, loses 2 electrons in its oxidation process. The sulfur gains 2 electrons in its reduction process, and we end up with an overall reaction that's entirely balanced. So it's correct mass and charge balance, right? Mass balance is when we're looking to see that we have the right number and types of species present on both sides, and then charge balance takes into account those transfers of electrons that happen in oxidation reduction processes. If we want to really follow this sort of process visually, we can look and see what happens when a zinc strip is added to a copper 2 sulfate solution. We can see that the zinc undergoes oxidation. We lose some zinc ions. That's a little tougher to see because we're not able to see at the macro scale the small number of zinc atoms that have gone on to form zinc ions. But if we look at the reduction half reaction, the copper ion gaining those 2 electrons to form copper metal is very visible. The strip gains that coppery color, and as you see in the last picture on the slide there, when you remove that zinc strip, it's now coated in a very, very thin layer of copper, metallic copper, because of the reduction of the copper ion from solution to form copper metal on the zinc strip. what we see on that zinc strip on the macro scale is very good evidence of that electron transfer. But if we want to think about it at the smallest level, at the level of atoms, we can see that copper 2 ion coming into the zinc surface that's full of zinc atoms, elemental zinc. As that copper ion deposits on the zinc strip as copper metal, now those 2 electrons that were generated by the zinc atom becoming zinc ion can be transferred to the copper ion to form that copper metal. And we see we still have the same number of atoms there on the zinc strip, but they've changed identity. We have a copper ion has become a copper atom, and a zinc atom has become a zinc ion here. This seems like as good a time as any to check on how your understanding of this oxidation reduction process is going. So let's pause here for a learning check. Your challenge is to identify each of the following reactions as either oxidation or reduction. These are actually what we call half reactions. They're just showing half of the story. And so it's up to you to decide, is the reaction showing the oxidation process or the reduction process. Please pause the video here, and when you're ready to check your work, start it back up again and we'll see how you did. All right, so in that first case where we start with the tin metal and we form tin ion plus 4 electrons, well, since we're losing electrons, we're going from a 0 charge to a +4 charge, or 4+ charge. We're moving to the right on the number line. Those are all ways to talk about oxidation, right? The loss of electrons is oxidation. Moving further to the right on the number line for the oxidation number is another example of oxidation. So hopefully you were able to identify that for number 1. Number 2 and number 3, the giveaway probably is the electrons being on the reactant side rather than the product side as in the first example. So hopefully you identified that both of those reactions, 2 and 3, are showing reduction. In number 2, it's the iron 3+ ion gaining 1 electron to become an iron 2+ ion. Again, we're moving from a more positive to a less positive number, and therefore moving to the left there on that number line is a reduction process. And then for the third reaction, we have the chlorine, diatomic chlorine, right? A molecule that's made up of 2, just like oxygen and nitrogen and the other of the 7 total diatomics. So chlorine's gaining 2 electrons to become 2 chloride ions, which are -1 each. We're going from a 0 oxidation number to a -1 oxidation number, and therefore we are undergoing reduction, the gain of electrons. If this is not making a lot of sense yet, please do try some additional problems. Reach out to me for some help, and we'll do our best to get you to master this somewhat difficult at first concept of oxidation reduction reactions. First, however, let's follow up with another learning check. So in this example, we're looking at light-sensitive sunglasses. So these, you've probably seen them on the market. They've been around for some time. The UV light initiates an oxidation reduction reaction where silver ion and chloride ion are reacted in the presence of UV light to form silver metal and chlorine atom, a chlorine radical actually, because we know chlorine should be a molecule with Cl2. So your challenge here, identify which reactant is oxidized and which reactant is reduced. So please pause the video now, make your selection, and then start it back up to see how you did. So hopefully you correctly identified the chloride as the species getting oxidized, right? It goes from Cl- to the neutral chlorine atom plus 1 electron. So that's a loss of electrons, therefore an oxidation process, and it's the UV light that causes that to happen. Therefore, the only other reactant is the silver ion, and that must therefore be reduced. That's what's gaining that 1 electron to go from silver plus 1 ion to silver metal. So again, it's a fairly unusual process because it gives us that chlorine atom as a product, and we know that's not stable, and that's why they are temporary states, the UV light initiating that formation of the silver and chlorine free atoms, and then in the absence of the UV light they go back to the silver and chloride ions, which is what they prefer to be at room temperature and pressure. But anyway, hopefully you were able to identify the oxidation and reduction of each reactant in this example. Let's try one more learning check for this topic. In this learning check, you're going to identify the substances that are oxidized and reduced in each of the following reactions. So for reaction number 1, you'll identify which reactant is oxidized and which reactant is reduced, and then you'll do the same thing again in reaction number 2. So please pause the video now. It'll probably take you a few minutes to work these out, and then when you're done, start back up and we'll see how you did with this learning check. All right, in that first example, we had the magnesium starting off as magnesium metal and going to form magnesium 2+ ion on the product side. So as well as the ion, it must have also released 2 electrons to do that, and that's an indication of oxidation, right? Magnesium is oxidized because it's losing electrons. The H+ ions are being reduced to elemental hydrogen. They're going from a +1 to a 0 state, and they're gaining electrons, 1 electron each, for a total of 2 electrons to make each H2 molecule, and that's a reduction process. So the magnesium metal is oxidized, the hydrogen ion is reduced. In our second example, in that reaction, it's the aluminum now that's oxidized, aluminum metal going to aluminum ion and releasing 6 electrons in the process for every 2 aluminum atoms that undergo that oxidation. Loss of electron, oxidation, right? The bromine is being reduced from Br2 to Br-, and so therefore that's going to have to happen 3 times and require a total of 6 electrons in order to balance out the aluminum that we had 2 moles of aluminum forming 2 moles of aluminum ion and 6 moles of electrons, right? We have to get our electrons to cancel, and with Br2, we're always going to need an even number. With aluminum, we actually generate an odd number, 3 electrons for every aluminum. That's why we had to adjust the coefficients in order to get total balance for our chemical reaction here. But that's a little beyond where we are right now. Right now, as long as you could identify which species is oxidized and which species is reduced in each of these examples, you're in a good place for now. Okay, I mentioned at the beginning of this topic that this is very important in biological systems. So typically in biological systems, we don't have a whole lot of metals becoming ions and ions becoming metals. That's just not how our physiology tends to work. So a couple of things to keep track of if you're looking at oxidation and reduction in biological systems. In the case of oxidation, typically you're looking for the loss of hydrogen or the gain of oxygen, right? Oxidation makes sense that it would be involving oxygen. So those are 2 ways to look at that process in biological systems. For reduction in biological systems, typically it's the opposite. It's either the gain of hydrogen or the loss of oxygen, or both of those processes happening for the reduction half. Now, of course, the definition is still the same. Oxidation involves the loss of electrons, reduction involves the gain of electrons, but whereas in pure chemical systems, we tend to deal with elements going to compounds. In the case of biological systems, it tends to be compounds remaining compounds, but forming new and different compounds, typically by the loss or gain of hydrogen or oxygen. We could have picked any number of oxidation reduction and biological system examples, but here we happen to be looking at some biomolecule that's reacting with the coenzyme FAD. So that biological molecule is going to transfer 2 H's to the coenzyme, and therefore it's going to be oxidized. The biological molecule itself is oxidized because it's losing hydrogen. It's also losing electrons as well, but again, in biological systems, we tend to follow the hydrogens more than the electrons. And we also have the coenzyme FAD being reduced to coenzyme FADH2. So that's a reduction. It's the gain of 2 hydrogen as well as the 2 electrons that accompany those hydrogen. So just to be aware that you're likely to follow it with atoms instead of electrons when you're dealing in biochemical systems, and this is an example showing that. So let's end this topic with table 6.4, which gives a nice summary of the characteristics of oxidation and reduction. Again, oxidation always involves the loss of electrons, whether you remember it as Leo from Leo says Gur or oil from oil rig. That's always true. In biological systems in particular, we'll often be following the addition of oxygen or the loss of hydrogen for that oxidation half reaction. For the reduction half reaction, it always involves the gain of electrons, whether that's the Gur from Leo says Gur, or the rig from oil rig, or however else you've determined to memorize that. You'll always be right about that. In biological systems, you'll often also be seeing a loss of oxygen or a gain of hydrogen for that reduction half reaction. But again, it's always true to say that a reduction half reaction involves the gain of electrons. We just happen to see that biologically often as the gain of hydrogen or the loss of oxygen. All right, so there we go. Again, unfortunately not the easiest subtopic here in Chapter 6, but an important one, and hopefully one that through the learning checks we did together and the homework that you're looking at and other additional end of chapter problems and reaching out to me for additional help where needed, you'll be in a good place not only for the upcoming exam, but also for what you need this course for in your future goals.